I did, but I didn't have a chance to look at it.
All right, let's get started. We have the current complexity homework that is due tonight. We have a homework coming out today on sorting. I will also reveal the next assignment for the next week so that you can start thinking about and working on recursion if you'd like to study that a bit on your own. We will be, as soon as we're done with insertion sort and bubble sort, we will be talking about recursion. If you are not super familiar with recursion, haven't done it a ton before, probably isn't best to just jump right into the homework. Wait for at least the introductory lecture, but I'll at least reveal the assignment so that you can take a look at it, think about it, practice it if you'd like to. But we should be getting to it with enough time to actually implement it ahead of the 8th. And if you'd like to get started on it, I'd be happy to take a look at your work, let you know if you're on the right track. Just get that feedback on recursion before you sit down and do something recursive on the 8th. Question?
Are we gonna touch on final IO later on, or is that?
My goal is to have a day or two before the 8th where we can just talk about what is it that people want to get practice with. That's where that would go, but there's no file IO in the curriculum of this course specifically. So that is something that you will need to study and hopefully re-study. Is it something you've seen before? Hopefully. If not, then maybe we can have an office hours session. If I can set a date that works for people that want to do that. Then we can just, anyone who wants to do file IO, we can do that in more detail in my office. Makes me miss Pullman. There's a bar called My Office. So you can always say, I'm going to my office. We need more puns around this area. So now when I say my office, I giggle inside like a little child and no one else gets it. It's so sad. All right, so fixed the issue with the code from yesterday. It was a very straightforward issue that I'm sad I didn't see in class. If current is equal to minlog, they're the same location and you want to swap here with itself. The math that you were doing was basically setting both current and minlog, both of those indices in the list, to the total. Then you go to subtract one from the other and you subtract something from itself, so you need 0. And then 0 minus 0 is also 0. So in that case, you were replacing the value that you wanted to swap with itself with 0, which is why we had 0 in the array. So a quick, if current is not equal to minlog, then do that. Otherwise, do nothing, and you've already swapped it with itself. That does work, and you can see that by running it, the 19 is actually there. So if you're going to do this, there is that one side case of when they're equal to each other, when you're trying to swap something with itself, you need to make sure that you're not doing this logic at that time. And then it works. Questions on that fix? How do we feel about insertion sort? Were we able to make some progress and mostly get it put together? No responses, a couple slight head nods. So I'm gonna guess that means most people didn't have a chance to get there. At the very end of last class, we were starting to write out what it would be like to write the pseudocode and replace the pseudocode with some code. So let's actually continue this process and then replace it with the code just to emulate that planning or design process. So we said with insertion sort, we're going to, outer loop is going to go over every element in the array, starting with the second one, that index 1, because the first one is already in order with respect to itself. But now we need to insert the second element where it goes in the sorted list. And then we will insert the third one where it goes in the list. So we want to extract the current element. And then we want to say something like from the current position back to the beginning, identify where this element goes. So inside of that, then we just need to make that associated swap once we identify. Is there anything else we need to consider? Or is this basically everything that we would care to? If we do this English logic, do we have insertion sort? Actually isn't even necessarily a swap. I think you use place, because you're making the hole for it, really. I think this is basically what we want to do. So let's try to replace each one of these lines with something logically that relates to it. Where do we want to start? When you have this design, it doesn't necessarily mean you need to start at the beginning. You can start at the most innermost idea, whatever is the innermost idea, and work outwards so that you have self-contained logic that's testable. You could start with the outermost logic that says, all right, when we begin this method, what's the first thing we need to think about that needs to be done? We have a little bit more flexibility when all of that design is on the page right in front of you. Maybe we should start by at least naming some variables so we know what because it's hard to write. Once found, place the current element in the new index. Writing that line without knowing exactly what the variables are is going to be challenging. So let's at least name some variables. Maybe to name the innermost variables, we should start with some of the loop definitions. So let's start here. What do we want to call this variable? So this is going to be the elements that we are currently looking at. Yeah. Cur. All right, where do we want to start cur at? 1. We said that we want this to be starting with the second element in the list because the first element's already sorted with respect to itself. So we can just do that. Cur is 1. Cur is, where is the last element that we want to swap back? You know, if we're using less than, then we're going to go up to and including the element before this and then stopping at the element that we're on. So we actually want the size. Why do we want the size, not the size minus 1? Yeah, the last element we want to work with is the element at index size minus 1. That is the last element in the list. Because we will still need to insert that. Once we get to list.size, that is the first index that is out of bounds of the list. We don't want to try to dereference that and say, what is at that position in the list? Because there's nothing there. Excellent. So this will be our definition. I'm going to throw this brace down underneath all of our. And this is the for each element in the array part. I'm just going to delete that. So the next thing we would want to do is extract the current element. What is the current element and what do we want to call that variable? Int, what do you call it? Temp. How do we get access to it?
Just not get it for
At the cur index, we want to do that. I'm actually, now that cur could stand for really anything, since cur is an index, I'm going to name it something relative to an index. Rather than it's a cur usually means a value or an object, whatever we are currently looking at, and not necessarily an index. So let's call this index. And in fact, if you haven't seen this before, let's actually go through, rather than change it in 4 places. You can just refactor. If you right click on it and say refactor, rename, this works in IntelliJ as well. You can see that what you're working with is a text box that is all of the associated text boxes of that. So if I call this index, now it's making the change in all of those places. Question?
Will that only do it in that function, or will it do it for any instance of curve?
Wherever that is defined to be. So yeah, all instances of that variable. If there is another one in another scope named cur, that is a different variable. It is capable of knowing scopes and what it's referred to. So yeah, to give you an example of this, let's say, since this index is defined inside of this loop, I can now make a new index outside of this. Let's say I make it double. In fact, I can make it an int. And then to show that that's the case, if I refactor this index, first of all, you can see that when it highlights only the same index, not the index that's defined down here. And then if I go through that refactor, rename, and try to modify this, it is only modifying the current scoped index. So it's a smart tool. Okay, so now instead of calling this temp, now we can call this something that's. This is the current value, so this makes more sense to be named something like current. So let's call this cur. This is the current value that we are inserting into the sorted array that is ahead of this. So if that's extracting the current element, great. I think this is a little bit clearer, which is good. We need to go into another loop from the current position back to the beginning. We need to figure out where this element goes in the sorted list of all of the indices before the current index that we've called index. So what does this look like? Can we easily make this a for loop? Yeah.
Let's have a for loop that starts at wherever curve is, I guess. And then
Yeah.
move back.
You would have to find a way to break out of that because the condition for that would be until you reach the beginning of the list, but we might not be going that far. So rather than putting a break statement in a loop, which is pretty messy, in general, we like to avoid breaks and continues wherever we can. Whenever you're thinking, I should put a break in here, that's just an additional condition that should go in the loop definition. If there's a while or a for, the condition that is the middle condition in a for, or the condition of a while. So I'm going to structure this as a while because we don't know exactly how many times this loop is going to run. In general, if you know how many times the loop is going to run, if there's a variable for that, then you want to use a for loop. If you don't know how many times it's going to run, you want to use a while loop because that extra counting variable the for loop gets you is irrelevant. So let's go ahead and say while. So what is it going to look like when we have found what we're looking for?
For it to be greater than the.
So yeah, cur, this thing that we've stored is going to be greater than. Yeah, we're comparing this, we want to compare this to the element at the now current index into the list we're looking at as we go backwards. So how are we getting access to that? Yeah, there's definitely a list.get, but how are we getting this value? We don't want to compare index because index is already where we are. We can't modify index. There's some other variable we need.
Not sure it's necessary, but still be sworn as a second.
Yeah, you can certainly do that. Let's actually go ahead and do that. So. It is gonna create an out of bounds exception at some point. Is there any reason to think that this is giving us an index out of bounds exception? Since we're starting index out at 1. As we do this, we will certainly not have an index out of bounds exception. Index -1 will always be in bounds. Yeah,
If we have an empty list.
if we did have an empty list, that would be bad. So maybe that's something we check for as an exception. We can't insertion sort an empty list. Would index starting at 1 be less than list.size if list.size was 0? 1 less than 0. I would argue that this for loop won't even run. So I don't even think we need the ability to try to throw that exception, because in that case, this entire loop's not happening, insertion sort does nothing. You've sorted a list of size 0. Very good to be thinking about, but I think we've actually handled it, which is nice. So now we don't want this to be indexed. Let's start by looking at prev. This value that we have said is the element at the index before what we are looking for, or looking at. Question?
Would it just be pre then, not list get pre?
Yes, it is just prev. We're not storing an index here, we're actually storing the value. Do we want to store the value? I think actually we want to modify this parameter. So maybe we just say this is index -1. And then we do say this is list.get. Because we're going to want to mess with this here momentarily. Let's do that. That's going to work out better for us in the long run. Does it make sense what I did? Just going from accessing the element at that to talking about the index. Because the index is going to be what we want to decrement to always access the element of the list at that index. All right, inside of this, there's actually one other condition we want to include here. Because we want to stop this once we are looking at the beginning of the list. So how could we make a Boolean expression that says, and we are still in bounds of the list? Yeah.
It is greater than or equal to 0.
Yeah, so we could say and prev, since it's an index, is greater than or equal to 0. We could do that. Excellent. Inside of the while loop now, we want to actually do, since we know the comparison, we know that this was true. So we're ready to continue to bump down until this is false. Once we've identified that, then we know the associated index where we want to make the change. So all we want to do inside of this loop is what is it? What's the one line?
If or is less than.
We already know exactly, we already know that it's greater because of the entrance condition to the loop. Yeah.
List set. Swap it out.
So we would be doing that, swapping it backwards. So all we want to do is we want to make room for it by moving. And then once we are done, we have that hole that we want to put the element in. So we actually don't even need to modify anything with the list. We're just trying to identify where does it go. So yeah, I guess yes, it is 2 lines, but we do need to do. Yeah, we're gonna end up, it's gonna be prev because we wanna modify, yeah, where we're going. So it is 2 lines. The last one is prev minus minus. But we were onto something here where we need to actually make one change to the list. We need to move the element of what we're currently looking at one forward as we start to make room for the current. So the first time we do it, we're overriding that value that we've stored. Let me actually draw this out. We drew this out last time, and I think at this point it's getting complicated enough that we actually need to visualize what's going on. So we want to. This is the current element we are on. Here is some other useless sorted stuff. So we have 1, 2, 1, 3, 4, and we're on 2. So we're trying to, we've stored off this 2. As we did right there. Let's not get indexed. So cur is now this 2. As we're moving this back, we basically want to say, here's list.get cur. This is that index. So yeah, list.get of the index. We said prev is this value right here. So we're comparing 2 to 4, saying, is this greater than, is 2 greater than 4? Oh, sorry, while cur 4 is greater than list.get a prev. While 2, yeah, it should be less than, shouldn't it? While cur is less than. Excellent point. While 2 is less than 4 currently, then we're going to overwrite this with this value. So we want to take what is stored here and override it to that. And we're going to continue to do that process until we've made a hole where 2 can be inserted. That's the name insertion sort. So the only element that's left to do here is the logic that is the overriding or replacing of what's pointed at by prev needs to go to what's pointed at this list.get index. Yeah, so we're gonna do list.set because we're doing an override, right? So the first thing set takes question.
So, well, not a question, I think I finally figured out what you're driving at. I think it should be list.set pre plus 1 should be set to list.get pre.
Yeah. Yeah, we want to set the index of current, wherever current used to be pointing to, list.get index. Starting at index, but then it's going to be that element as we start to move backwards. So we want to set at index prev plus 1. And we want to set it to be the value that is list.get of prev. Question?
Why can't we just use index instead of prev plus 1?
Because as this shifts down, where you end up wanting to write is no longer index. It's always prev plus 1, which will be diverging from where index is. So index is always pointing here. And prev is pointing here, so the first time we want to write index, but then prev is going to move to point here. So we want to write this 3 here, not here.
Yeah.
Any other questions on that? I think this will work. So we want to set to prev plus index prev plus 1, the value of the list at prev. Then we want to decrement prev to be pointing at the previous index in preparation for the next pass through the loop. Question?
How are we saving the index of the number that we're getting rid of? So like, or that we're replacing them to in a sense.
Yeah, that's an index.
That is okay, so index is what's storing the data.
Index is what's storing where we are in the list. Cur is what's storing the data.
Okay.
So, yeah, index is currently where we are in the list. Cur is the data at that place in the list. And then prev is the previous position in the list to where we are currently looking to insert. It's not the previous place to index, that's just where it starts. Because we continue to bump it backwards inside of this while loop. Once we've done all of that, all we have to do is insert the extracted value where it goes in the list. What is that one line? So all that's left in all of insertion sort is this one line. Once this loop terminates, we know we've made that hole where cur should go. So current is that value. We want to make sure that we're storing it at the appropriate place in the list. Yeah,
Let's not set pre plus one.
let's not set the index that we want to set is, yeah, it's prev plus one. The prev was decremented in anticipation of running through the next loop. So where we actually want it to be, where we want to insert is at prev plus one. It's great. What do we want to put there?
Sure.
Yeah, that value we stored off before. That should do it. Let's test that out. So I will just write exactly the same main. In fact, I'm going to copy it over from selection sort. If I'm going to be doing some copying like this, maybe we should factor this out into our own class, but we're lazy for the moment. So we would expect this to provide a sorted array. We get an index out of bounds exception. We queried index -1 or index -1. Where did we do it? Right there. What happened? Yeah.
0, so it's still there.
Yeah, when we say prev is greater than or equal to 0, when we try to access prev minus minus and then come back around and say list.get prev. This allows me to introduce you to the concept of short circuit evaluation. I mentioned this to a few people in my office at one point, but the easiest fix to this is surprisingly just to swap the order of how this is evaluated. I run this, we see that it works. I made no change in the logic, and is a commutative operation, right? A and B is exactly the same as B and A. So why does this work when the previous one didn't? Does anyone have any insight into that, especially someone who was in my office and heard me talk about short circuit evaluation?
You get kicked out of the week before it tries to.
Yeah, so what happens here is, what do we know about what needs to be true for an and to be true? They both need to be true. What can we decide if we are an intelligent machine if we see this first element is false? It doesn't matter what the value of the second one is. So yes, it does not even run this code. So it does not even try to check list.getPrev. That would be index -1, but you can see that that isn't even run, that isn't even tried, because when this shouldn't be done, this is false. By recognizing that, you can actually order your Boolean expressions in such a way that if this is going to give you something that's out of bounds or something you don't want, make sure you check something that's not going to be out of bounds first. So that works. That's also true for ORs. What do we know about ORs? As soon as the first one is true, we don't need to check the value of the other one. An inclusive OR at least. So short circuit evaluation works for both ands and ORs. All right, so that is insertion sort. Any questions on how insertion sort works or why it works? Yeah,
Real quick, could you go over that last line, that last set that we did?
yeah. So let's even draw back that example that we had here. So as we're set up for this last insertion where we said we had 1, 3, 4. And we stored off 2. So this is what this looks like after the loop is complete. Is that this used to be where the 2 was, we wrote the 4 from here to here. Then we wrote the 3 from here to here. And there's still technically a 3 here. But we're gonna treat this kind of like a blank. We've made the space now for this 2. So this 2 needs to go where it's supposed to go in the sorted. So we're trying to write this here where there is a 3, but for all intents and purposes, it's a useless value that we don't care about because the 3 is actually stored there. We duplicated this 3 into that spot. They used to have a 4 in it, but we moved that here. That overwrote the 2, but we stored that here. So how do we store this 2 in this location? We want to set, because remember the last thing we did was we had prev set here. And then we decremented it in preparation for the next pass through the loop. So prev is pointing at this index. So we want to set to index prev plus 1. The value that is stored in current, which is what we stored away at the very beginning of the code. So that number that we stored off, we found the place that it goes. The place that it goes is at prev plus 1. So that's where it should go. That makes sense to everyone else too? So I do a lot of work that probably could be done on paper, just in my head as we're coding, but drawing this out is very useful for understanding exactly what's happening and exactly how all the code ties together to do the more complicated thing that is insertion sort. All right, let's analyze the complexity. In the worst case, what is insertion sort? Thinking of the worst way that we could put the underlying data, be that in reverse sorted order, totally random order, thinking about what order of numbers would cause this method to perform the worst, to have the hardest job sorting the numbers. What would that underlying? We have 1 vote for reverse sorted. What is that? If it was reverse sorted, how much work would we have to do? What would it look like to sort the list? Yeah, we don't ever get to stop early, right? This while loop is saying we can stop early if we find where it can go. And if it's reverse sorted at every single index, we want to put that all the way at the beginning of the list. All the way at the beginning of the list. It's the new smallest value, all the way at the beginning of the list, which means that we're making space across the entire array for every value that's in the array as we sort it. So that is quadratic in nature. So the worst case for insertion sort, just like with selection sort, is quadratic. How about a best case? Thinking of the underlying structure of a list and the actual code that we wrote. What is the best way that the underlying data could be to minimize the time that it takes for insertion sort to run? Yeah?
It's already sorted, would it be linear?
Yeah, if it's already sorted, this is actually linear. Does it make sense how it's not quadratic if it's already sorted? If we have a small list that is just something like 1, 2, 3, 4. We're at the 1. We say that's already sorted. We start at the 2. we go into this loop condition and we say, is this value less than list.getPrev? No, loop over. 3, is 3 less than 2? No, loop over. Is 4 less than 3? No, loop over. We see how this is linear. We're asking one question for every value in this list. We never have to overwrite, make a place for it, insert it, because it's already in order. So the best case is not quadratic. The best case is actually linear. Because we have differences between the best case and the worst case, what is the average case? It's no longer obvious. We can't say, since the best case and the worst case are the same order, the average case has to be that order as well. We now have a disagreement between the best case and the worst case. Is the average case some order between those? Is the average case one of those cases? Does anyone have an argument for what happens if you were to call insertion sort on 10 random lists? How much time would it take? Is it more like the worst case, more like the best case, somewhere in between them?
More like worst case.
More like worst case? What makes you say that?
Odds on it's not sorted.
Yeah, odds are the list is not already magically sorted. What if some of them are almost sorted? If it's almost sorted, is it closer to linear or quadratic? Be closer to linear, maybe? How, according to all lists that can be ordered in any way, how many of them are sorted or almost sorted? Not very many compared to those that are random or closer to reverse sorted. Yeah, that ends up being right. If you think about an average value, how far do we have to move an average value to get it in place? So let's say something like, we've gone through all of the work and we're looking at this last element, trying to figure out where it should go. And here we have this length, we'll just call it something like capital L, that is the length of the array that this needs to go back somewhere in. Would we agree that if this list is randomly sorted, it's equally likely that we need to make space for it at any position within L? It's just as likely to have to go all the way to the front than it is already sorted at the very end. So how much space should we expect it to have to go back? It's about L over 2. That would be the average of how much work has to be done. It would be just a uniform distribution of where it should go across every possible index in L. So on average, it has to move L over 2. It's just that this L scales to be the portion of the list before the current index. So we get something like, it's going to have to do half the work of 1, followed by half the work of 2, followed by half the work of 3, followed by half the work of 4. So it ends up, this L over 2 is the equivalent of, when you boil it down, 1 plus 2 plus 3, up to n. When you do all of that, this half just shows up consistently, so you divide the whole thing by 2. For the amount of work of how far back do we have to go. Instead of having to go all the way back for every time, which gave us this 1 plus 2 up to n, now we have to go half the way back. So for each one of these terms, we divide it by 2, which means we can just throw it under the whole expression. But since it's a constant, it doesn't change the order. So since this was quadratic, this is quadratic. So the average case of insertion sort is quadratic.
Does that go back to our n squared plus n over 2?
Yeah, this would be the n squared plus n over 2. It was an extra n over 2 now, or over 2, so it would be n squared plus n over 4. Rather than over 2, but that's still just a constant. So average case involves a lot more thinking and a lot more work about how much work is happening on average, but a lot of the times it doesn't actually change the underlying order. So the important takeaway is worst case quadratic, best case linear, average case quadratic. Yeah,
Those would all be in big O notation.
yeah. Yeah, we're just talking about the order here. We're not talking about anything, analyzing every one of the lines, coming up with a full function. This is just the reason we can compare selection sort to insertion sort and say that they're equivalently bad. Is that the worst case and average case performances of both are quadratic. Yes, there's this nice best case behavior with insertion sort if the list is already sorted, but that happens so infrequently that it's irrelevant in the general case. However, if out and about in your future career, you think there's a reasonable chance this list is already sorted, that might cue you in that you could consider a sort that has a best case behavior on arrays that are already sorted. It would give you a reason to use insertion sort over selection sort. Sometimes we'll get better performance, and based on this, it's likely that that best case is going to happen more frequently than it happens randomly. There's always critical thinking. All right, so that is insertion sorts analysis. So we're going to start talking about bubble sort. Yeah.
In the case of, like, you do have a best case scenario, and you know that best case scenario can happen, it would be better just to prepare for the worst and expect the best.
Yes. Yeah, just knowing that it can happen would not ever make me use insertion sort over selection sort by itself. Since I still prefer selection sort, I find it easier to write. A best case linear would not make me switch. All right, let's talk bubble sort. All right, bubble sort is certainly the most fun to watch of these sorts. But to me, it's the least intuitive of these three and the most obnoxious. So of course, it's the one that appears the most on the ape. If you're gonna know one sort through and through, it's probably good to know improved bubble sort. We're going to start with talking about bubble sort, and we're going to start talking about, is there an optimization that we can make to this? Because it turns out that bubble sort by itself can be improved. But let's take a look at the pseudocode and try to understand what's going on. All right, so bubble sort takes in some list of sortable items. Makes sense, any kind of list, could be an array list, could be a linked list. We are going to store off the length of that list. We can, in Java, just access the size of the list. We're going to go into a loop. We're going to set some Boolean that we're going to call swapped to false. We are now going to go through the list and determine if the current pair is out of order. So looking at the element before A of I and comparing it to A of I. If they're out of order, we're going to swap them, but also remember that we swapped something. We're just going to continue that loop until we stop swapping. Then we're going to reset and do it again, and do it again, and do it again, until we go through an entire pass through the loop where we did not swap anything. Once we didn't swap anything, we know everything's in order. So what this looks like is we're just continuously starting at the beginning of the list, going all the way to the end, looking at pairs of numbers. We're looking at these, and then 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 these. Swapping them if they're out of order. If we made a single change, we start back at the beginning and ask the same question. Start back at the beginning, ask the same question. As soon as we make no changes, we're done. So let's go ahead and give you an example on the board. This will be plenty of board space. Let's go right there. Okay, so we have a little bit of time to explain this. We'll make this long enough that it can showcase exactly what's happening. 7 elements. As always, I need some numbers. Let's make this interesting.
26.
Yes. Next.
48.
48, 85. Great. Next.
1.
1. Love it. Next.
32.
32. Next.
7.
Yes. Next.
1.
1 again. Fascinating. Okay. With the first pass, we're gonna start looking here and here. Luckily, we don't have to keep track of any index. We're just gonna repeat this logic over and over and over again. Question? Yep, we're gonna check and see if these two numbers are out of order. If they're out of order, we're gonna swap them. Is 26 greater than 48? No. Moving on. Actually, I should also have a swapped. So currently, that starts out at false, saying we haven't made a single change. All right, 48 and 85, they out of order?
No.
No. Moving on. Are they out of order?
Yes.
Yes, we're gonna swap them. We're gonna set swap to true, because we made at least one change. Next. Moving on to the next two, are 85 and 32 out of order? Yes, we're gonna swap them. Moving on to the next pair, are 85 and 17 out of order? Yes, we're gonna swap them. Moving on, are 85 and 1 out of order? Yes. All right, we've reached the end of what we can compare. What can we say about the state of this array after a single pass through using this concept of swapping those that were out of order? It's a bit better, yeah. 1, 2, 3, 1.
Not yet sorted.
Not yet sorted. Yeah, we're not done after a single pass. That's good to know. Yeah, yeah, largest is at the end. That's a big piece of information. Is that always guaranteed to be true after this first pass?
Yes.
No,
Wait, yeah, that's where the sort of.
Yes, it is guaranteed that your largest element is in this spot.
oh,
It is not guaranteed that the smallest element is in this spot, but whenever we found the largest element, it was always out of order with everything that came after it. Once we found that 85, we kind of scooped it up and just kept swapping it all the way to the end of the list. So this is guaranteed to be in order. Great. Next. We're gonna do it again. We reset and set swapped back to false. We haven't made any changes. Out of order?
No.
No. Out of order?
Yes.
Yes. So we're going to swap 1 and 48 and set swap to true. We made at least one change. Moving ahead. Out of order?
Yes.
Yes, we're gonna swap 32 and 48. Out of order?
Yes.
Yes, so we swap 17 and 48. Out of order?
Yes.
Yes, so we scooped up the 48 along the way and kind of carried it along to the end. But the other things that are smaller are slowly bubbling their way back toward the beginning, thus the name bubble sort. The bubble that is the largest thing bubbles its way to the top. Think of it like a bubble in a drink. It moves its way to the top. And it displaces everything that it moves past backwards, one spot. And some things get bubbled backwards a couple times when you find the second largest element and move that forward until you find the largest element, and you'll leave the second element there, second largest element there, grab the largest element and move it. So everything that needs to go back toward the beginning of the list is making at least one move toward the beginning of the list, and the next largest element is being found and moved toward the end. So we are just about out of time. Any questions on the concept of bubble sort? If we finish this, do we agree that we have a sorted list? Once we didn't actually do this swapped, once this was false. All the way through, the list would have to be sorted already. All right, we'll pick this back up and have you implement this first thing tomorrow. My office hour starting now. If you have any questions on the homework, the 8th, or anything else going on.